We're now going to look at some practice problems. Yay! We only have a couple of examples that we're going to work with, but that's all right. Okay, suppose the system has this transfer function, g of s is equal to 1 over s. Then the system is not bibostable, because if we apply a step input, remember the step input has this Laplace transform, 1 over s, and so you get 1 over s squared occurring. 1 over s squared occurring. The inverse Laplace transform of 1 over s squared is y of t is equal to t. That's not bounded. It continues on. It blows up. Now it doesn't blow up exponentially, but it does blow up. So the system is not bibostable. Suppose now we consider this transfer function, 1 over s squared plus 1. That has eigenvalues at plus and minus j on the imaginary axis. Plus or minus 1j. So I have eigenvalues on the imaginary axis. This system also is not bibostable, since applying the sine wave, u of t is equal to sine of t, we would get basically, so this, the Laplace transform of this actually is this quantity, and so we get s squared plus 1 quantity squared, which gives us repeated poles at plus or minus j. And when you take the inverse Laplace transform of that, this is the response you get. Again, we have t times sine of t, so t again continues to increase. So this is a sinusoid that continues to increase and blows up. So these two systems are not bibostable, or they're not p-stable for any p. Okay, because the output y is going to have norm that's infinite, and the input norm is going to have norm that may not be infinite. So basically, for a system to be bibostable, it has to have the poles of the system have to be completely in the left half plane. Okay, entirely in the left half plane. They cannot even be on the axis. If they're on the axis, we can always find a bounded input like a unit step. Remember that the origin is on the imaginary axis. Or we can find a sinusoid that has poles on the imaginary axis that match those poles. That's a bounded signal that gives an unbounded output. Okay, so they have to be strictly in the left half plane. They cannot be on the imaginary axis. Obviously, they can't be in the right half plane, but they need to be strictly in the left half plane, not on the imaginary axis. All right, now suppose we have this transfer function matrix. Okay, and we can see the poles of this are strictly in the right half plane. The left half plane. But if we take the inverse, so this is a single input, two output system. If we take the inverse Laplace transform of each of these guys, that gives us the impulse response. And this is the response that we get. So I've gone through and done the partial fractions. So notice even though I have repeated poles, they're stable poles. So I have, for example, t e to the minus t. So even though t looks like it would be blowing up, e to the minus t is decaying, and it decays so fast that this term dominates this term. And so this whole term goes to 0. And so we have this expression. We go through and compute the integrals. Okay, we can go through and compute these integrals, and this is the value we get. We go through and compute these integrals, and this is the value we get. And so when we look at this nasty formula, in this case, I have the maximum for i's, so of the rows of this sum. So in this case, this is the summing along the rows. In this case, we only have summing along columns, we only have one column, so we don't really need to do that summation. And since we only have two rows, then this nasty formula boils down to this. This quantity is just the sum of these two guys. Is the maximum of these two guys, which is this one. and that's finite. So our system is bibostable. Okay, so this is just proving that our system is bibostable. Of course, we already knew that since we could look at the poles and the poles were strictly in the left half plane, then our system was bibostable. So we didn't have to go through all this computation. But this is just to show that in general, if my system is not linear or time invariant, then we could still use this formula to check to see if it is bibostable. In that case, it's going to be a nasty check, but this is one way to check it. So this is bounded input, bounded output stability.